Okay, so I just started the recording. Can everyone hear me?
Yes.
Good, good. And can everyone see or maybe I should say, can anyone not see all the shared screen? This area?
I can see it.
Okay. Well, thank you all for coming and for making the decision to be here live. I think, you know, the big advantage of that is that you can ask questions. So definitely interrupt me anytime with questions, or just, you know, I guess there's those little hand thingies, symbols, or just say, excuse me, or something. Really, because that's a huge part, right, of the live, or later in person, eventually again. Does anyone have any questions or issues that have come up before I get started? So the quiz will be posted tomorrow at noon on Canvas. And I've decided to do quizzes this way. And then there'll be a 24-hour window. So they'll be due Saturday. This will be shown on there, due Saturday noon. So it's essentially a take-home quiz. And the upload of the completed quizzes should be scanned and uploaded into Canvas. So if there isn't already a place to put that, I think there is actually. I'll check. Please try to make clean scanned copies, not murky, grayed out photos from a distance or something. You know, like we've all been doing the online stuff for a while. So if you have any questions on ways to scan, there is, if you haven't already used it, there's an app called Cam Scanner that a lot of students like. Basically, you can use your phone to scan into a PDF to make a multi-page PDF. So I will, and I'm going to re-announce all this, but please have a multi-page document, not 4 or 5 attachments that are separate pictures. I'll send out a detailed announcement on all this. And as far as the session videos, there was this whole snafu earlier this week. So I think they will stay in Canvas for a day or two, probably. But like I said, you want to get to those. If you want to go and re-review this session, of course, you're all here. So this is more applicable for the people who are not here. But then later it goes to this program called Panopto. And there's a menu item link to that. You could try that. Otherwise, I'm going to continue to put them on YouTube because it's way easier, I think, than messing with Panopto right now, and perhaps more reliable. We'll see. So, any questions on that? I need to move this. Okay. Today's a little bit of a catch-all of topics where we're at. We're transitioning a little bit into the next unit, and things will start to pop up for chapter 13 in Canvas now that we're at quiz time. So getting ready for the next unit. Thought I would go over a little bit more nomenclature. So just in a way as reviewing perhaps. So find the longest, most substituted chain. So if this structure on the left is the one we're trying to do, you can count along 1, 2, 3, 4, 5, 6. That would be a hexane with 2 substituents, one there, one there. And then you see maybe there's an equally long chain here, 1, 2, 3, 4, 5, 6. So that's a hexane with one substituent on it, this group, which we would call an isopropyl group, right? So find the longest most substituted chain means that this first one I counted, 1, 2, 3, 4, 5, 6, would be the most substituted because it has two substituents. So this is an hexane. And then I might have done this exact example before. And then at the 2 position, there's a methyl, and at the 3 position, there's an ethyl group. If you imagine the squiggly lines dissecting those bonds. So 3 ethyl, 1 methyl, going alphabetically E before M, and hexane, and not, I'll put not 3 isopropyl and hexane. I will point out that 3 isopropyl and hexane conveys the same exact knowledge, to be honest. But there would be cases where an incorrect name would lead you to draw a different structure, which would basically be the definition of an incorrect name. Here's another one. So all I did really was add another couple of carbons in these positions. And so now we're looking for the longest, most substituted chain again. We still have the 1, 2, 3, 4, 5, 6 that pops out. But then look, upon adding carbons, I got the 1, 2, 3, 4, 5, 6, 7. So that's the longest chain wins out, definitely. So that's an N-heptane. They all end in ane because they're alkanes. No double bonds, no triple bonds, no other functional groups, which would change the name, like an alcohol. And so with that longest chain, we have 1, 2 substituents, and I think I know what caused that, or maybe not. That's really weird. Well, there's the other substituent. So hopefully this is not going to continue doing that. So at the 1, 2, 3, 4 positions, puts those 2 substituents at the lowest combination of numbers, rather than if I numbered it from the other end, for example. Bear with me here. Okay, so 5, 6, 7 to complete that. So we have a methyl group at 3 and an isopropyl group now at 4. Indeed, an isopropyl group. So 4 isopropyl, 3 methyl, and heptane. Any questions on that? Maybe if I do, I think it's a virtual memory problem in part, possibly. RAM. So rings. I didn't show a lot of examples with rings, and so we have here a cyclohexane ring. Cyclohexane. So instead of hexane, it's cyclohexane if it's in a ring. Try one other thing here. Yeah, I think, okay, so, and then when you number substituents on a ring, so there's 2 methyls, and so it's going to be a dimethyl cyclohexane. Dimethyl. And you would say 1, 2, 3, 4 dimethyl. So 1,4-dimethyl, the methyls, which is, there's a little bit of redundancy. You could say 1,4-methyl, but it sounds a little weird because if methyl is singular, you know, sort of. So you put the dimethyl in there. However, if you build the model of this, you will quickly see that what I pointed out in one of the other videos was that the ring isn't flat appearing like this as we're looking at it from the top right now. If you look at it from the side, end up looking at it from the side, it takes on this flex conformation that looks something like this. And at the one position, you might have a methyl sticking straight up, and you might have another methyl at the 4 position. So 1, 2, 3, 4. And you're not gonna be asked to draw this right away, but so those are your 2 methyls. Notice that they're both basically on the top face of the molecule. However, there's another version of this that, and I'm drawing these to try to help get closer to the real shape of the molecule. There's another version of this where one of the methyls is pointing down like this, and the other one is unchanged. 1, 2, 3, 4. So this is also 1,4-dimethyl, but these are different molecules because, again, by definition, there's a hydrogen here and a hydrogen here. And I would have to detach this and switch them and then reattach them to get this. So because they're different molecules, as we saw with all the isomers, which these are isomers, we have to have different names for these. And so if they're both on the top face of the molecule, like this, we call that cis, basically meaning on the same side. And then if they're on opposite sides of the molecule, one on the top face, one on the bottom face, we call it trans. So bottom face, top face. So on opposite sides. That's an E. Cis and trans, especially important for rings. And then if we wanted to draw this in a simpler way, because normally chemists wouldn't draw these conformational diagrams every time, we could simply do this, going back to this. And if I wanted them to be cis, I would point them both up like this using the wedge, if you remember the wedge and hash marks. Also, I suppose I could do this where they're both on the same face. But actually, if you flip this over like a pancake, I'll say pancake flip, you can easily go from one to the other. So these are the same, cis. So these go along with each other. And then the trans, as you can easily guess, is going to be one up, one down. And there's really only one version of that. I mean, even if I, well, in this case, if I, might as well do this. If I do this, actually, this is just rotating without flipping. Rotate without flipping. So cis and trans. So cis and trans are different molecules and isomers. These are not conformational changes. They're different molecules. I should write that. Not conformational changes. So to come full circle, 1,4-dimethyl cyclohexane as a name is incomplete. If I come up to you on the street, or if you come up to me on the street and say, hey man, you got some 1,4-dimethyl cyclohexane? I'll be like, which one? Right? And you'll be like, oh man. So you have to say cis 1,4 or trans 1,4. Cis or trans, oops, for completeness. And so, okay, so any questions on that? Pretty straightforward. We can actually emphasize this. There we go. So this is the trans. So it's always good to have other ways of looking at it. Like at first it's like, whoa, but here you can see, if I flip it this way, you can see the 6-membered ring in the middle. You can see how it's flexed. Interestingly, notice like these hydrogens here are all on the same top face and pointing straight up, and then these ones on the bottom are pointing straight down. There's actually a term for that called axial. And then the methyl groups are sticking out to the sides, but even though, like, notice this methyl is only slightly up and this one's only slightly down, they're still on the top face and bottom face, respectively. So this is the trans 1,4-dimethyl cyclohexane. And then I have the cis. And this is where the models really, you know, it's amazing, right? Because there's the ring in the middle. You can see the same ring. Somehow I can't rotate it with more level, but this is the cis. The cis doesn't look quite like we expected, does it? One of the methyls is straight down, but in order for the other one to be cis, it can only be partly down because of the way this flexes. So these are the kinds of things that are revealing when you build your own model. So chemists really like lots of different ways of representing things. Got some more stuff coming up. Okay, so also in Unit 1, changing gears slightly, but we're going to come again around to the concept of isomers and geometry and so on. So more functional group recognition. This molecule is called actinocytine, if I spell it right. If I can spell it right, E-C-T-E. I think that's the spelling. Again, it's a cancer compound, cancer active. I'll just say anti-cancer. When you say anti-cancer, it means that it at least kills cancer cells in test tubes, in vitro. If you say anti-tumor, that means it actually has anti-tumor effects in a tumor in a living organism. So it's kind of like anti-cancer comes before anti-tumor. Not sure this was ever proven to be anti-tumor. It might have been. I don't think it ever made it through clinical trials, though. It had some promise. So functional groups in blue, alcohol, right? Anyone want to venture to say what this functional group is? Oh, wait a second. So, you know, hopefully we want to get to the point where these are very quickly recognizable. This is an amine. And then over here we have an ether. It's the edge of the screen. I'm not sure what the deal is over there. It's getting, yeah, I don't know what's going on. Here we have a sulfide. This whole thing. Sulfur, oops, it's doing that again. Sulfur bounded by 2 carbons. Over here we have an ester. And then here we have a benzene or aromatic ring. Benzene unit aromatic ring. Okay. So one thing I can point out with this amine, there's different, like with alcohols, there's primary, secondary, and tertiary amines. So this amine is actually a tertiary amine. Tertiary amine. So I find it better to introduce concepts as we see them. This is a bit of a preview for later when we do amine chemistry. We'll rehash this. But amine, primary, secondary, tertiary is a little different. So a primary amine is defined based on how many carbons that nitrogen is attached to. So if nitrogen is attached to 1 carbon, then it's a primary amine. And then if the nitrogen is attached to 2 carbon groups, for example, carbon, carbon, this is a secondary amine. And attached to 2 carbons. This is okay there. Technical stuff. Clearly, a nitrogen attached to 3 other carbons is a tertiary amine. And attached to 3 carbons. So unlike alcohols that are defined by the number of carbons that the alcohol's on are attached to, the amines are defined primary, secondary, tertiary by how many carbons the nitrogen itself is directly attached to. So back to this nitrogen in the diagram in the structure is attached to 1, 2, 3 other carbons, so it's a tertiary amine. Little digression there. So the expectation is that when you get these fundamentals down, we can start combining concepts. Really, starting to get into more of the science rather than particular individual details. So how many isomers are there of the amine C5H13N? Now, the fact that there's a nitrogen in there makes it different from any of the problems like this that we've done so far. So it brings in the concept of primary, secondary, and tertiary amines, and how amines bond, how many bonds a nitrogen can make, and then the rest of the same concept with drawing different isomers. So clearly the easiest way to start is to draw your first straight chain compound, including all the atoms at first, just to convince yourself that they're all there. 5 carbons with 4 bonds to each carbon to complete any bonds remaining with bonds to hydrogens. 1, 2, 3, 4, 5 carbons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, yep, matches the formula. And so, and this is a primary amine, right? The nitrogen attached to only one carbon. So, from our earlier practice with isomers, we know that an easy way to make isomers is just to start branching the carbon chain in different places. So first I'm going to redraw this in the condensed structure form, because to me it's way easier than having to draw all the carbons and hydrogens. 1, 2, 3, 4, 5 carbons. So I know I can make a 1, 2, 3, 4, 5 carbon version. So that's very much like what we've already done with these kind of problems. And then that sends me on my way with other versions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? These are different. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's another different one. 1, 2, 3, 4, 5. That's a different one. There's going to be a lot. 1, 2, 3, 4, 5. That may be all that I can do in that way. So another leap of insight is necessary here to find more, because there are more isomers of this. These are all primary amines because the nitrogen is attached to only one carbon. So if we remember that, oh wait, there can be secondary amines, meaning the nitrogen can be attached to 2 carbons, carbon there, and then we need more carbons. So 1, 2, 3, 4, 5. This has 5 carbons. 1, 2, 3, 4, 5. And then it's like, okay, well, we're back to the straight chain. These are secondary amines now. Keep that the same. 1, 2, 3, 4. 1 is 5. And there's another one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I think that's all the secondary amine versions. Oh, no, it's not. Because I can go 1, 2 on one side and 1, 2, 3 on the other side, H. And then I can do 1, 2 on one side and 1, 2, 3 on the other side. Now I think that is now all the secondary amines. And then to make a tertiary amine, 1, 2, 3, 1, 2, 3, 4, 5. And that has so all of these nitrogens have, in addition, one lone pair. Remember all those. So this is the only one, there's only one tertiary amine version of this molecule. And some people might ask, okay, well, wait a minute. What about if it's like this? These are the same. So and if you want, you could build the model of this to convince yourself that these are the same. But for now, you can just believe me if you want. They're the same through rotation, right? If I just rotate the bottom one slightly in this direction, I get the top one. So I'm not having to disconnect any bonds or anything like that. So when we introduce a functional group like an amine into these kinds of isomer problems, it reinforces the whole concept of isomers, the concept of how bonding is allowed around an atom like nitrogen or oxygen. And it gets us to thinking about all the different, permutations and shapes of things, and having to decide if two things are the same or not the same. Any questions on that one so far then? Okay, so now we're starting to, I want to begin to segue into the next topic a little bit. This is often I will cover this topic earlier, but with the new book, it doesn't really go into it except in bits and pieces later. But it's pretty critical in organic chemistry, the geometries of these single, double, and triple bonded compounds. In other words, alkanes, alkenes, and alkynes. Which I have shown. But it's more than that. The amines above are not alkanes, alkenes, or alkynes, technically, right? The amines that I drew above are single bonded compounds, though. So they share that with alkanes. So this is just for starters. The simplest alkane, remember, was methane, and originally we drew it like this. But then I pointed out, when we saw the 3D structure of methane, we drew it like this, with this coming toward us, toward, and away. Yeah. Away. And something that I haven't brought into the picture yet, which I'd like to do right now, this is dramatic footage of a methane. So the carbon is at the center, the hydrogens are the blue coming in and bonding. And what we're seeing actually are called orbitals. So these are really getting closer to the shapes of the molecule itself as defined by clouds of electrons, where the electrons really are. The nuclei are buried way deep inside. So it's kind of interesting to see something that is a little closer to reality. Believe it or not, this is even closer to reality. I'm pausing there. When you really calculate with supercomputers, basically nowadays, the shape of a molecule, taking into account the electron clouds, where the electrons could be at any given time, it looks something more like that. And you see the methane now on the interior represented. Oops. Now I'll jump back to the beginning. There. So you see our methane hidden in the middle there. And notice the red is higher electron density regions. The red regions are high electron density because they're the regions of methane. And to do that, the regions of methane where the bonds are, because bonds are what? Electrons. Bonds are just electrons. So we can take a look at ethane, ethene, and ethyne in this way. So ethane is an alkane. Ethene is an alkene. And if you recall, it has one unsaturation, which we define basically as removing 2 hydrogens from the alkane version. Gives you one unsaturation. And then the ethyne has 2 unsaturations, like this. And I pointed out earlier that this is linear, trigonal planar, and I mentioned tetrahedral, great word. Tetrahedral. A tetrahedron is like methane. This has tetrahedral. So these are geometries. As defined by where the electrons end up in those clouds that you saw. And it's probably a good idea to point out some of the bond angles. So the bond angles in a tetrahedron, so the bond angle, like this angle, is the bond angle, is 109.5 degrees. That's the one that's a little harder to remember. The others are easy to remember, as you'll see. So all of the angles around this carbon are 109.5 degrees, which we saw clearly in the videos that I just showed. It's because all the electrons repel each other. You may recall this from Chem 111, BSEPR, valence shell, electron pair repulsion. You know, the electrons in the bonds especially are repelling each other to get as far apart as possible. And with 4 things, the way that things can get as far apart as possible is to form a tetrahedron. With only 3 bonds, essentially, or 3 directions to point around a carbon, the angles are 120. They're all 100. That's the degree. 120 degrees angles. And then the geometry of a linear molecule is clearly 180 degree angles. Thus, we get linear, trigonal, planar, tetrahedral. So planar, meaning if I was to draw this with more sort of perspective, say use the wedge and hash mark, which is not a great thing to do on these, to be honest. It can lead to some confusion. But for this example, it's okay. It's like the hydrogen here is coming toward you. This one's away from you. It's flat. It's flat in a plane. So it's planar. It's a flat molecule. This has big implications for reactivity. And so does the fact that this is linear. So, but linear just means it's like a line, right? Questions on these so far? And we can take a look again at some videos. So ethane. Okay, so it's like 2 methanes coming together, except you'd have to remove a hydrogen from each one in the middle and replace it with this bond here. Okay, here come the hydrogens of ethane. Notice it's a tetrahedron. Each carbon is a tetrahedron. Each carbon has 4 groups around it, and those groups point as far apart from each other as possible. And then here we go with that electron shell, electron filling space filling model is usually what it's called. Oh, that's behind now. Okay. Do this. And again, it's going to show you, there's our ethane molecule, how it looks like the ball and stick, like our models. Go through that. We can go through that one more time. So alkanes, basically all tetrahedral geometry, fully saturated, all 109.5 degree angles, all tetrahedra throughout. And space filling, electron density, same deal, in between atoms mainly. So I'll point out that an amine is also tetrahedral, even though it doesn't have 4 things bonded to it. It has 3 things bonded to it, but the lone pair would be the other corner of the tetrahedron, also tetrahedral. And again, this has strong implications for its activity and reactivity. Alkenes starts to get really interesting. I feel like using the class time for this is good because of the video aspect and visuals and so on. Being able to provide something that you can't get necessarily reading the book. So alkenes, this is going to have some surprises. Okay, so what on earth are the yellows? The yellows are the origin of the second bond of the double bond. They're going to form that double bond. And so what is really amazing here is the green is essentially carbon-carbon, single bond, carbon-carbon. The second line that we draw as to make a double bond is in reality is these clouds of electrons both above and below, bringing in the 4 hydrogens of ethene. Now this is looking at it from the top. It's going to rotate. And if I stop it there, we're looking at the plane of the molecule. We're like in flatland, in the plane of the molecule. And above and below, you have these clouds of electrons, and you have electron covalent bonds. All of these are covalent bonds, but they're different types of bonds. The green is one type of covalent bond. The yellow is a new type of covalent bond that we've only up to now just drawn as a second line, believe it or not. And then you can see it from different angles. I'll replay this one more time. The electron space filling model. Now this introduces something very different because of this analysis. Notice the electron density is in red, and it's way above and way below, corresponding to those yellow areas. There's the flat ethene molecule. Let's see this again. Single bond forming. Second, double bond forming. Hydrogens. Side view, end view, electron density view, high electron density in the middle, above and below. So when we look at ethene and draw it like this with the two straight lines, that's a complete abstraction. It's a notation. It's barely a notation. We have the single bond framework of ethene. And so this is a covalent bond of two electrons being shared. The pi bond, as it's called, rests above and below as clouds, which you have to consider this a single unit, actually, which is why we only draw one additional line to represent it instead of three lines, right? So, and even more mind-blowing, these two electrons can be here, or one could be here, one could be here, or the two could be down here. And so the question immediately comes up is like, how does an electron get from up here to down here? Because what these are calculated probability areas where those electrons could be at any given time. And so in between, there's zero probability that these electrons could be there. How does an electron get from here to here if it can't ever cross over directly through nothingness? All of this is quantum chemical, quantum mechanical, high math sort of calculations. But the best theory currently is that for an electron to get from here to here, it has to leave our dimension, go into another dimension, and then come back out again. Mind, period, blown, period. Now, alkynes, like ethine, also have this same abstract notation, like three lines. But so now we know that those three lines are not the same thing. One of the lines is your single bond, like that, and the two hydrogens. The other two lines are another bond like the one we just saw, above and below, and then another one. I should use a different color. Oh, I'm running out of time. Another bond in front and in back, hard to draw, where there's another two electrons. And we have just time, I think, to see this video. I don't remember, I think this is the last thing for today. So this is alkyne. Two carbons, single bond forming, double and triple bond forming. The two hydrogens come in on the end. Notice it's linear geometry. Basically looks like a pig in blanket. End view, electron cloud view. On the last, so even more to the point of where the electron density is all around the middle for that double and triple bond of the alkene. There's the linear molecule shown in the middle. Show it one more time. And then I do have a final point to make based on all this, because this really segues into our next topic and then into start to understand reactions. (180 degrees). Knowing where that electron density is especially important. So the final point to make here based on all this, how did that get moved? Final point based on all this. So next chapter is going to be alkenes. and I'm going to start posting stuff for that soon. Alkenes, and, I want to say alkenes and alkynes. Okay. Y-N-E-S. I'm at the bottom of the page. An alkene, like ethene, let's just say any alkene. Remember, the electron density was high in the middle for that extra bond that was in yellow before. So maybe I should have done yellow. These electrons are reactive electrons. And why did I draw an arrow? The arrow represents a bond breaking. Likely to form, likely because it is forming a new bond. From one of the carbons to something else. And so we're going to find out that this, because it's our understanding of structure and bonding, like you just saw, how the electron density is piled up here in the middle for alkenes and alkynes, these double bonds can break and then form a new bond from one of these carbons to something else. So we're going to see that in the next chapter. And sorry, 2 minutes over, but thank you all for coming. If there's no, I'll pause for questions here. If not, I'll end the session. Any questions?
Sir, I had a question.
Yeah.
This might be really simple, but when we were going over ethane with the tetrahedral,
Yeah.
I know with the way that it's written out, I don't know if it's possible or not, but like for just writing it down, could you do like C and then that single bond and then another C and then have the H3 on both sides, or is that not possible?
So over here, so like ethane, if I'm hearing you right, CH3 like that on one side, you said?
Yes, sir.
And then I would, if I was drawing the other side, I would just do this. But were you actually saying, can you do this and leave it like that? Or?
Yeah, like the top one is, could you write it like that, or do you have to draw out the entire structure?
Oh no, I would most often write it like this, probably. And I think I would only write it like this because because really in the condensed drawing system, it's really just a line, right? But that's a little bit uncommunicative. I mean, that's subject to misinterpretation maybe. So I think I would always draw ethane like this, but as soon as you add another carbon like propane, I would draw it like that, and probably not even include the C's and the H's or the 3's or any of that, just because it's so much quicker, than doing. I mean, you could draw propane like this. I think I would do it like this, and a lot of people will do this, but I kind of don't like that. I often tend to do this for clarity. But you could do that one I just showed too. Yeah. The one thing not to do is to mix, to leave off things, like to leave it like that, or to make up your own system where you do this. I think I pointed that out earlier. It's mega annoying. So yeah, that's probably a longer answer than you wanted, but.
No, that's perfect. Thank you, sir.
Okay, well, thank you again all for coming, and I guess I'll end the session here.
Thank you.
Have a good weekend. Good, and don't forget the quiz. Okay, so.
Thank you. Have a great day.
Hello, Professor.
Oh yeah, do you have a question?
Yeah, so you said the quiz is due Saturday?
Yeah, it'll be assigned. It'll be posted on Canvas tomorrow at noon.
Okay.
And it's this basically take-home quiz. You have 24 hours to do it, so it'll be due noon on Saturday. But certainly you could turn it in anytime before that.
Okay, so I have a slight issue because I'm on the football team here and we travel to Montana tomorrow and we'll be on the road for 6 hours and we have a game tomorrow. I mean, we have a game Saturday at 10 a.m. And with meetings and all that, I really would not have time to complete that assignment.
Okay. Let me get back to you on email. Is this Nate?
Yes.
Yeah. It's really. Let me get back to you on email rather than talking in front of other students about it.
All right. Thank you.
All right. Look for my email. Yeah.
Okay. Thank you.
All right. Okay.